You probably already know that everything is made up of little tiny things called atoms. You might
Just confirming, the audio is coming through from the tab, because it's not showing my little audio button.
might even know that each atom is made up of even smaller particles called protons, neutrons, and electrons. And you've probably heard that atoms are small. But I'll bet you haven't ever thought about how small atoms really are. Well, the answer is that they are really, really, really small. So you ask, just how small are atoms? Well, to understand this, let's ask this question. How many atoms are in a grapefruit? Well, let's assume that the grapefruit is made up of only nitrogen atoms, which isn't at all true, but there are nitrogen atoms in a grapefruit. Well, to help you visualize this, let's blow up each of the atoms to the size of a blueberry. And then how big would the grapefruit have to be? It would have to be the same size of, well, actually, the Earth. That's crazy. You mean to say that if I filled the Earth with blueberries, I would have the same number of nitrogen atoms as a grapefruit? That's right. So how big's the atom? Well, that's really, 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 really small. And you know what? It gets even more crazy. Let's now look inside of each atom. That's the blueberry, right? What do you see there? In the center of the atom is something called the nucleus, which contains protons and neutrons. And on the outside, you'd see electrons. So how big is the nucleus? Well, if atoms are like blueberries in the Earth, how big would the nucleus be? You might remember the old pictures of the atom from your science class where you saw this tiny dot on the page with an arrow pointing to the nucleus. Well, those pictures, well, they're not drawn to scale, so they're kind of wrong. So how big is the nucleus? So if you popped open the blueberry and were searching for the nucleus, you know what? It would be invisible. It's too small to see. Okay, let's blow up the atom, the blueberry, to the size of a house. So imagine a ball that is as tall as a two-story house. Let's look for the nucleus in the center of the atom. And you know what? It would just barely be visible. So to get our minds wrapped around how big the nucleus is, we need to blow up the blueberry up to the size of a football stadium. So imagine a ball the size of a football stadium, and right smack dab in the center of the atom, you would find the nucleus. And you could see it. And it would be the size of a small marble. And there's more. If I haven't blown your mind by now, let's consider the atom some more. It contains protons, neutrons, and electrons. The protons and neutrons live inside of the nucleus and contain almost all of the mass of the atom. Way on the edge are the electrons. So if an atom is like a ball the size of a football stadium with a nucleus in the center and the electrons on the edge, what is in between the nucleus and the electrons? Surprisingly, the answer is empty space. That's right, empty. Between the nucleus and the electrons, there are vast regions of empty space. Now, technically, there are some electromagnetic fields, but in terms of stuff, matter, it is empty. Remember, this vast region of empty space is inside the blueberry, which is inside the Earth, which really are the atoms in the grapefruit. Okay, one more thing, if I can even get more bizarre. Since virtually all of the mass of an atom is in the nucleus, now there is some amount of mass in the electrons, but most of it is in the nucleus. How dense is the nucleus? Well, the answer is crazy. The density of a typical nucleus is 4 times 10 to the 17th kilogram per meter cubed. But that's hard to visualize. Okay, I'll put it in English units. 2.5 times 10 to the 16th pounds per cubic feet. Okay, that's still kind of hard to figure. Okay, here's what I want you to do. Make a box that is 1 foot by 1 foot by 1 foot. And let's go and grab all of the nuclei from a typical car. Now, cars on average weigh 2 tons. How many cars' nuclei would you have to put into the box to have your 1 foot box have the same density of a nucleus? Is it 1 car? 2? How about 100? Nope, nope, and nope. The answer is much bigger. It is 6.2 billion. That is almost equal to the number of people in the Earth. So if everyone on the Earth owned their own car, and they don't, and we put all of those cars into your box, that would be about the density of a nucleus. So I'm saying that if you took every car in the world and put it in your 1 foot box, it would have the density of 1 nucleus. Okay, let's review. The atom is really, really, really small. Think atoms in a grapefruit, like blueberries in the Earth. The nucleus is crazy small. Now look inside the blueberry and blow it up to the size of a football stadium, and now the nucleus is a marble in the middle. The atom is made up of vast regions of empty space. That's weird. The nucleus has a crazy high density. Think of putting all those cars in your 1-foot box. I think I'm tired.
I like this particular TED Talk. It really is a good representation and a nice mental image of how small we are talking about when we're talking about atoms, because we're really talking about something that you can't see. We don't even really have microscopes that are strong enough to zoom in and actually see the atom, let alone many of the subatomic particles. We can see the effect of some of the subatomic particles, but we can't actually see the particles. I rewound, whatever. Backed up for just a couple seconds to the illustration where it's showing the marble and the football stadium size blueberry. So if the nucleus is the marble in the blueberry, so very, very small marble in a rather large space, the rest of that space is where the electrons are found. It's our electron cloud. You will see a couple of different illustrations of the atom, but this is a good way to visualize the relative size of everything. So if you've ever been to, like, I know technically Turner Field is not football. What is the new Falcons Stadium called? I don't know. Anywho, if you've been to most any professional stadium, you can kind of visualize how big that stadium is. And if in the center you had a very little marble, that would represent the nucleus, and all of the other space would represent where you could actually find your electron clouds. And I forgot to silence my phone again. There we go. Okay. Switching when I'm sharing, 2 moments. No. There we go. So today is our first lesson on the atom, atomic structure, and periodic table. This, as I said earlier, is a rather short unit. If you look in your Google Classroom, you have your typical note-taking, I don't want to say outline, but that's the only word that's coming to mind, that you are highly encouraged to use. Some of this might seem familiar to you because you have seen this in 8th grade physical science. In addition to notes in this entire unit and the next unit, you're definitely going to want your salmon colored reference sheet. We are officially moving away from the formulas, and we're moving to the periodic table side of this particular reference sheet. This reference sheet has been added with the resources for Unit 5 in Google Classroom, as well as another color-coded periodic table that is more up to date than the Georgia Milestone one, because they don't have all the elements correct names that were updated like 4 years ago. Yeah, 4 years ago now, I think. So today is all about the atom. The atoms are the basic building block of matter. Atoms make up everything that you encounter. It is the smallest unit of matter. Sorry, I lost my pen. That retains the same properties. So when we're talking about an element, if we have a pure sample of an element, it is only composed of one type of atom. And every atom of the same element has the same number of protons. The protons determines the identity of the element. So if I want to know which element I'm playing with, I look at the number of protons, or I count my number of protons. Protons equals your identity. We can't mess with the protons in the nucleus. We will not do nuclear chemistry. We can mess with electrons. We really like to mess with electrons. We will see how much we mess with electrons later in this unit, and definitely a whole bunch in the next unit. But those protons are what tell us which element we are playing with. Now, in terms of their locations, so we kind of, the previous video tried to illustrate their size, but in terms of their locations and their charge, We know that our proton and our neutron live in the nucleus. So that was that marble for the end of the video. And the proton and the neutron have a weight of 1 atomic mass unit. So atomic mass unit is what we use to measure subatomic particles' masses. It is technically defined as 1/12 of a carbon-12 atom, but you don't necessarily need to know that. It's really, really small. And electrons, it would take about 2,000 electrons to equal the mass of 1 proton or 1 neutron. So essentially, we say that electrons are massless. Now, in terms of their charges, our protons are positive. Protons are positive. My neutrons are neutral. And my electrons are negative. So I think of it this way. It's positive to have protons. It's negative. It's bad to get hit by electricity. And neutrons are just kind of neutral. You will see Miss Rains when I abbreviate protons, neutrons, and electrons. I will give you their little charges with that symbol. It's just a short hand way of writing stuff out. So, as I mentioned earlier, our electrons live outside the nucleus. They live in what we call the electron cloud. Now, there are several different models of the atom. We actually, in physical science, don't get to the current. We don't really use the current model of the atom too terribly much. But Bohr's model is probably one of the ones that is the easiest for high school students to conceptualize and actually. And the neat thing about Bohr's model is he's trying to illustrate how the electrons arrange themselves in that electron cloud. So for Bohr's model, we're going to show the protons and the neutrons in the nucleus. Sometimes this is just done with different colored spheres. Sometimes this is done with an actual, P equals 5, N equals 6 to tell us what is in the nucleus. But sometimes you'll actually see colored or spheres with charges on them. But our electrons are shown to live on specific energy levels, basically rings around the nucleus. And yes, I drew it up too high, so I can't show all the rings. So with these energy levels, there is a specific pattern in how the electrons have to go. And yes, you guys and gals do need to know this pattern. On the first energy level, the one that is closest to the nucleus, it can hold at most 2 electrons. I need to draw one more slightly blue circle. So at most, this first energy level is going to have 2 electrons. Really and truly does not matter where we put the electrons as long as they're both on that first ring. The second energy level can hold at most 8 electrons. And yes, I would normally want them spread out to show them up at the top, but since I drew my thing too big, we're just showing them all at the bottom part of the atom. So first energy level can hold 2, second one 8, third can hold at most 18. And for my few children out there who really, really like math, there is an actual mathematical equation that determines the number of electrons. So 2n squared with n being my energy level. So if I'm in the third energy level, 3 squared is 9 times 2 gives me 18. That's where that 18 comes from. I could do the same thing with my fourth energy level. 4 squared is 16. 16 times 2 gives me 32. The fourth energy level would have at most 32 electrons. You're never going to be asked to draw beyond that third energy level simply because Bohr's model doesn't really work under all situations. It worked great for hydrogen and helium, but it kind of started falling apart when you got to lithium and beryllium, and really, really fell apart when you got to group 3, period 3 elements So if we were to see Bohr's model for nitrogen, somebody telling me on our periodic table what element is nitrogen? Do I have? Haha, I do. For those of you who do not have your salmon colored periodic table handy, there is the PDF copy. You have to scroll to see page 2 for the periodic table. What element number is nitrogen? That is what I'm wanting somebody to type or talk and tell me. Can I put it on the screen? Maybe. Ew. I just realized that the physical science version of the periodic table does not let y'all actually search for elements, which is very, very sad. Let me make certain our extra one does. Open in a new window. Okay. Stop sharing for just a moment so I can show y'all a little bit of online learning hack. I'm not entirely confident why it doesn't work with the milestone version of the periodic table, but it does work with our additional one, and you are allowed to use either or on a test or quiz. I need to share a tab. There we go. So if you look in Google Classroom with the Unit 5 resources, you'll find not only links to the Safari Montage, which is our textbook for Henry County Physical Science, as well as links to Georgia Virtual Textbook. And you'll also find a PDF that looks really, really similar to what's on the screen. We gave y'all this particular PDF because if you were in a face-to-face classroom, you would have a color-coded periodic table on the wall. Well, we're not face-to-face most days, and our counterparts across the hall don't even have a periodic table at all. So we give you this one that's nice, pretty color-coded, just like the one in your traditional high school classrooms. So I had asked y'all what number was nitrogen. With this version of the periodic table, if you bring up the PDF version of the document and hit Control F, it gives you the ability to find things on the document. So I want to find nitrogen. So I'm just going to start typing NIT. I don't even have to spell the whole thing out. Just if I put NIT and I hit enter, it will highlight nitrogen for me. So you can kind of see it in green on the screen. If it wasn't on the screen when I went and searched for it, I believe it will jump you straight to it. No, it would help if I could spell. There we go. So if it's not on the screen, it will take and jump you straight to it on the screen. So looking at this periodic table, nitrogen is element number 7. I know that because that is the number above its symbol. The other piece of information that we are given on here besides the symbol and the name is the atomic mass. On both of our tables, whether it's the salmon one or this color-coded one, the number is on top and the average mass is always going to be on bottom. If you look at some other periodic tables online, they do sometimes flip those numbers around, but we try to be consistent. I need to share a window. There we go. So nitrogen was element number 7. Well, if we look and we count in Bohr's model of nitrogen, we can see that we have 1, 2, 3, 4, 5, 6, 7 protons. This thing has 7 protons. Remember, I said the protons were the identity. Additionally, I can see that if I were to count the green spheres, it has 1, 2, 3, 4, 5, 6, 7 neutrons. Not all elements have equal numbers of protons and neutrons, especially when you get above element, I think it's like number 20. They don't have equal numbers of protons and neutrons. And our electrons are shown on those rings. If we count, we can see that we've got 1, 2, 3, 4, 5, 6, 7 electrons as well. That entire blue space is trying to represent the electron cloud, and the little circles are representing the rings that Bohr thought the electrons traveled on. We now know that the electrons don't travel on rings in predictable orbits, but it is a good way to visualize the amount of energy electrons have. So in your chat, GoGuardian chat, tell me what each part of the atom is on my illustration. Which particle represents which part of the atom? GoGuardian chat or Google Classroom comment if you are not a Chromebook baby. I got to get back to the assignment so I can actually see Google Classroom comments. If you're not confident on all of them, at least give me ones that you think you know. It is okay to be incorrect. Why am I not? There we go. You're telling me which particle each thing represents, Cyrus. The A, B, and C, what are they trying to point to? Except for we're supposed to be typing it in GoGuardian chat. And I've hit GoGuardian chat on myself. I heard it ding. There it is. Dadnabbit. I did not mean to close GoGuardian completely. I meant to just minimize it so I could see what I was typing. Give me 2 moments, ladies and gentlemen. I accidentally just closed that window. So, ooh. Thank you, Joseph. Thank you, Mackenzie. Julius. Thank you. Layla. Thank you, ma'am. So you do, a part of our standards is being able to identify the position, the charge, and the relative size of our subatomic particles. Thank you, John. So in terms of size, this particular model does not illustrate their relative sizes. A should be considerably smaller than B and C if we were trying to show their relative sizes. What this does show is their charges and their position. So yes, my lovelies who responded in the GoGuardian chat and in the Big Chin Meat chat, yes, A represents my electrons. They are negatively charged. They live out in the cloud. The only thing this model does not show is the fact that they are about 2,000 times smaller than the protons and the neutrons. I think it's technically like 1,840, but it takes a whole bunch of electrons to equal the mass of one proton and one neutron. So if we look at B, B is pointing to this particle that has no charge. The only things that have no charge in my nucleus are my neutrons, which means C is trying to illustrate my proton. If we look, this particular atom with 4 protons is illustrating beryllium. So the 4 protons is telling me we were referring to beryllium. If I had something that was marking the entire center, that would be considered the nucleus. And yes, I know I did not have that on this particular model, but just throwing it out there. Oh, I forgot that it highlighted. So atoms are composed of identical protons, neutrons, and electrons. The way we tell them apart is by their number of protons. The protons equals the atomic number. My protons equals my atomic number. So earlier we saw that nitrogen was element number 7. My protons always equals my atomic number. Now, because most elements are neutral, most elements don't have a charge, that means my protons also happens to equal my electrons. Now, we can gain or lose electrons, but most of the time when we're talking about a normal neutral atom, the protons equals the electrons. So a couple of examples, if you were to look at your periodic table, you'd see that carbon, who is atomic number 6, has 6 protons. Phosphorus, is P, atomic number 15, has 15 protons. Gold is one of the ones whose symbol does not match its name. It is AU, and it is atomic number 79, and it has 79 protons. And if these were neutral atoms, my electrons would be the same. Because in order to have no charge, my numbers of positives and negatives must match. Now, the mass number gives us the sum of protons and neutrons. My mass number is my protons plus my neutrons. It's also a way that we can identify if we have an isotope. Like, for example, normal oxygen has a mass of 16. But the one on my screen is oxygen 18, and that is because it has extra neutrons. It is an isotope, and therefore its mass is more. Mass number, we do not give you on the periodic table. What we give you on the periodic table is called the average atomic mass. But sometimes they do give you the mass number with the name, like they did with these. So oxygen 16. Now, our periodic table is organized by atomic number. And when we put elements in order by atomic number, we have a repeating pattern in their properties. I don't know if y'all noticed in the periodic table I had up earlier, but you know what, I'll actually do it in red. All of these elements that I'm drawing a red box around were all red on that periodic table that I showed y'all earlier where you could hit the whole Control F. If we notice, most of our red elements are on the right side of the table. That's because that's where we mostly find gases. Not only does it tell us information about the physical or chemical properties, but it also tells us information about the energy levels, as well as the number of valence electrons. Oops. So what do these things mean on our table? This particular one is flipped from what we would normally see. We normally have our symbol above the name, but otherwise the information is still the same. My atomic number is always going to tell me my number of protons. And if we have a neutral atom, it's also going to tell me my number of electrons. I can use the average mass to get my number of neutrons. What we do is we round the mass to a whole number, and we subtract the atomic number. And that would give us our number of neutrons. So specifically, since I've got helium that I'm drawing on, if I were to look at helium, helium's mass is 4.0026. Well, I'm going to round that to a whole number, which is 4. 4 minus 2 tells me that helium has 2 neutrons. So I'm going to pick on iron for just a second. I know that mass is tiny, but it is 55.845. I want to round this to a whole number, which basically means I have no numbers after the decimal. So back in middle school or elementary school, we learned how to round. If the number after the decimal is 4 or less, then that would stay a 5. If the number after the decimal is a 5 or more, then the number rounds up. So we actually have a mass. My average mass would round to 56 minus the atomic number. This has 30 neutrons. Protons equals the atomic number. Electrons equal the atomic number. Neutrons equals my mass, rounded to a whole number, minus the atomic number. Every time. Now, if you notice on your salmon-colored periodic table, you have a key or a label up there. You can add extra information to that key. So y'all says it's helium, it's gold. But it reminds you that it's the atomic number. And you could add a reminder yourself that your atomic number equals protons. You could also add a reminder to yourself how to get your neutrons. So like I said, on ours, the symbol and the name are flipped. We will always tend to have our symbol above the name. It is important that the first letter of your symbol is uppercase and the second letter is lowercase if there's two letters. Otherwise, you may not be saying what you think you're saying. So my atomic number equals my protons, and if neutral also equals my electrons. Oops, I thought I fixed this. Apparently I did not. There we go. Now it's all on the screen. So all of that information is given to you on your periodic table. You do not have to memorize it. You just need to know how to use it and get it from the periodic table. So in GoGuardian chat, which element is being represented by this model? In GoGuardian chat, which element is being represented by this model? Oh, no. So in the GoGuardian chat, which element is being represented by that illustration for Bohr's model? Okay, it could have swore it said that he was coming in. There it is. Thank you to whomever responded in GoGuardian. Which element is represented by that model? Thank you to my second student. Really? Really? Well, I don't think I spelled specifically right. I'm hoping it's close enough. So which element are we illustrating below with this Bohr's model? Everyone should have out a periodic table. If you were missing your salmon colored one, here's the link a second time. Although I guess I probably should link the other one because that one you can at least find stuff on. I closed it. Bad Miss Rains. So to figure out which element, we have to look at our number of protons because the protons are the identity. And I can see that we have 1, 2, 3, 4, 5, 6, 7 protons. We have 7 protons. There's only one element that has 7 protons. That would be nitrogen. Because atomic number 7 means we have 7 protons. 7 protons means we are playing with atom number 7. Oops, not where I thought it was. Now, if I had 8 protons, it wouldn't be nitrogen, it would be oxygen. If I had 8 electrons with 7 protons, it would still be nitrogen. It just would be a nitrogen ion. If I had 7 protons and 6 neutrons, it would still be nitrogen. It would just be nitrogen 13, an isotope of nitrogen. My protons determine the identity. If we change the number of protons, we are changing the element completely. Dadnabbit. Okay, so I would like y'all to navigate to, that is not what I wanted to do. To this simulation for a moment. And select atom. I'm presenting a tab. There we go. So this simulation, you are limited with your numbers of protons, neutrons, and electrons. But the way the simulation works is you grab the particles from the bottom and you put them into the model, and it will actually show you on the table what you are building. So notice as I put neutrons in, it doesn't show me anything on the periodic table. Do the same thing with electrons. As I add electrons, it doesn't show me anything on the table. If you're interested, yes, you can show your net charge and mass number, but you don't start making elements until you start adding protons. So right now I've got hydrogen with its 1 proton. And I actually happen to have a hydrogen with a -1 charge because I have 1 more electron than I should. So I could take out the electron, and now I could have a neutral version of hydrogen. Oh, cool. So not that you need to for this particular activity, but you can select stable, unstable. With it being unstable, basically that's telling us that hydrogen does not really exist like this. So I can take some of these neutrons out and see, okay, well, that version of hydrogen is stable. Even take another neutron out. That version of hydrogen is also stable. So I'm going to drop in 4 protons and 5 neutrons and 6 electrons. Four, 5, 6. So notice with 4 protons, it is highlighting element number 4. And since I have more electrons, than I do protons, I have a negative ion. I could take some of these electrons away, and I would see Bohr's model for the neutral atom of beryllium. I could take some more electrons away, and I would see Bohr's model for beryllium ion. So for our practice today, you are using the simulation to build 10 different elements. And then you've got, I think it's 5 questions. Yeah, 5 questions that you want to answer. If you can do it without the simulation, you are welcome to just use the periodic table to get all the information. You don't necessarily have to utilize the simulation, but the simulation can be helpful, especially if you're not confident in your answers, because you can always go in and start dropping in the particles and see if you're making what you think you are making.